So good morning and welcome back. It's about half time for this lecture course, and I decided that I would like to present one central physical, example that uses about everything we did so far. So it will be a very good exercise. A very simple example, but if you really carry this through properly, you'll see we'll really meet almost everything we did. And so this is, formally speaking, still part of this section on Lie groups and Lie algebras, because we haven't finished this section yet. But in a sense, it stands there as a half-time example. So it goes in this consecutive numbering 4.4, and it's the relativistic spin group. Which goes by the name of SL2,C. That's what the thing is called. And we will now really want to understand this guy and its Lie algebra in every detail very properly. Now, although I say it's a relativistic spin group, and it is, in order to really apply it to physics, we also need to study representations. We haven't done that yet, but I hope we'll get there. But alone to understand this group as a Lie group, and in order to derive the Lie algebra and so on, we've got to work a little bit. But again, it's very good exercise. So let's see whether we can carry this through just with what we have. Okay, so let's first start with the definition of this guy. And first and foremost, before it's a Lie group or whatever, it's a set. It's a set, and this set has a definition. SL2,C is the set of 4 tuples, okay, quadruples. But I follow tradition, and instead of writing A, B, C, D with commas in between, I write A, B, C, D as such a square scheme of numbers. But obviously, this is a 4 tuple because I always know the first, the second, the third, the fourth, okay? Nothing new. And it comes with a condition, and that condition is that, and it's, if it's a 4 tuple, it's an element of, I take the complex numbers to the 4th, but that obviously means Cartesian product, Cartesian product, Cartesian product. But not all of these 4 tuples. I have a condition. I impose the condition that AD minus BC B1. That's my condition. So obviously C is a set, this is a set, this is a restricted comprehension, there is a condition here. That's a set, right? And it's a subset, obviously, of what we denote by C4, which is the short form of this. And this is SL2C as a set. These are the elements of the set. There is nothing to be said beyond that about the set. Well, but now we make the set into a group. And the group is then SL2C. A group is first and foremost a set, but then it has a group operation which we call blob. And this blob is an operation that takes two elements of SL2C and makes them into one new element of SL2C. And this blob is defined as follows. We take one element, which we decided to denote in this funny fashion. We take another one, A, B, C, D, E, F, G, H. And how do we define the blob? We define the blob by the following arcane construction. It's AE plus BG, AF plus BH, CE plus DF, plus DG, CE plus DG, and CF plus DH. Of course, it's easy to remember this because you have been trained to perform an operation called matrix multiplication, and it is exactly this. But what on earth is a matrix? It's a 4-tuple and another 4-tuple. We produce from it this 4-tuple. Don't think about matrix multiplication. It's just this rule of how to combine these tuples. And of course, what we got to check is whether this rule obeys this restriction, so whether the result is really, again, in SL2C. Now, it is, because you know this is matrix multiplication. We could now check this by hand. Well, yeah, you could. You multiply this with this, and you subtract this, and you'll reduce it. If you know that AD minus BC is 1, you know that EH minus FG is 1, you will find that also here this rule is satisfied. So this needs to be checked, but it, of course, applies. Or if you want to think in terms of determinants, of course, the product of two determinants, no, the determinant of a matrix product is the product of the determinants, so it will stay 1. Okay? So obviously, we have here a set, and we defined a very funny operation, but it provides such a map. And then you check that the whole thing is associative. This is now really boring. You believe me, it is. You'll check that there exists a neutral element. And this neutral element is 1, 0, 0, 1, as you can also quickly check, and that has AD is 1, aha, it lies in SL2C, very good. So there is a neutral element that looks like this, and you can also check that for every element small g, well, in SL2C, for every matrix A, B, C, D, you find an inverse matrix. Let's write it down. Okay, so for every A, B, C, D in SL2C, I claim, and you will quickly check, that 1 over AD minus BC plus minus plus plus minus like this, D, A, minus B, C. I think this is the inverse. Otherwise, you please look it up, but I think this is the inverse. This is the inverse, so we would denote this A, B, C, D inverse, of course, the formula 1 over determinant, and then this funny chessboard pattern, and then, but you take the transpose first, and then you do these minors and stuff like this. Okay, you know how that works. Okay, anyway, so for every element that exists an inverse element, you can quickly check that the inverse element has, again, AD minus BC is 1, because this is AD minus BC, but it's divided by this, so it's again 1. So also the inverse, of course, is an element of SL2C. So at this point, we learned, indeed, SL2C, this set, together with this operation, is a non-commutative, a non-abelian, but nevertheless, it's a group. Okay, fair enough. Well, fine. So, but now we come to the next step. I want to think about this group now, about the set that underlies the group, as a topological space. So let's think about the topological space, SL2C. Well, that's the set, so we need to equip it with some topology before anything else. So how do we do this? Well, we will always avoid constructing this explicitly. If possible, we inherit a topology from a space we know. C4 doesn't look so bad, but so far we took the real numbers. But of course, one of the things we can do, we can extend our techniques to the complex numbers. So first step, so C.1, if you want, is establish a topology or define a topology O sub C on the set of complex numbers. And we do this by virtue of the standard construction and that is defining, by virtue of defining the open balls. Open balls, well, that's just a name. The open balls B sub R, but now of a point Z in the complex numbers, and the R is still in R plus. And here we take simply, what do we take? All the complex numbers y, for which it's true that the absolute value of y minus z is less than r. And this is now, of course, the absolute value on the complex numbers. But obviously, this is if you go to the complex, plane, this is the point z. It's, well, without the boundary. It's all the complex numbers in here for a positive radius r. So you define these guys, and then the standard construction, you call a subset of C open if for every point of this subset there exists a positive real number such that the ball with that radius of that positive real number around that arbitrary point of D to be checked as open subset lies entirely within that subset. It's exactly the same construction like in R or in R2, okay? And obviously, this yields a topology on C. Further remarks needed? No. Or no? No? Okay, good. Okay, so we have this on C, but then very quickly, of course, if we have it on C, then we can define a topology on C in a finite Cartesian product, so on Cn, right, as the product topology. If I have one on C, I have one on C4 by virtue of the construction of the product topology. Okay? Now, so we have one on C4, but SL2C is not C4, but SL2C is a subset, is a proper subset of C4, of course, because it is C4 with a condition. Now, any subset can be equipped with the subset topology. So define this O by which we equip SL2C, define it as take the C4, so C, 4 times Cartesian product, that is what we constructed here, and restrict it to SL2C. Remember, that was the induced subset topology. Those were all the sets of the form U intersected SL2C, where U was open in C4, in C4. And then we have a topology, and we equipped SL2C with some topology. Very natural to do that, right? Okay. So now we have SL2C, a topological space. So you see, not a single technique we introduced was in vain, right? We need all of this. So now we continue. It's a topological space, but is it one of these particular topological spaces that we call topological manifolds? So check whether, or check that, so I assume the result. No, I don't assume the result. Anyway, check that SL2C with this topology we just constructed is a topological manifold. So what was that? If it's a topological manifold, that means by definition that around every point of this topological space you find an open set that you can map homeomorphically to some r to the d. Okay? Now here, of course, we can all do all these constructions and map homomorphically to some c to the d. Okay? And maybe one thinks, oh, it must be C4, but see, this is only a subset, and this condition kills 1 degree of freedom. So, and on the right-hand side, it's 1 plus 0 times I. So it really kills a complex degree of freedom. So we have the feeling this is complex 3-dimensional. But we don't need feelings. We can just construct this. I construct charts that cover the manifold, and where you have exactly this property, and if it covers, then you of course know you can do it for every point. So okay, so construct charts. Construct charts. And I think, well, we'll see how many we need. Let's see how many we need. Construct charts. Aha, okay, let me think. So the intuition is, but we're going to write it down exactly, intuition is I can kill one of the degrees of freedom in this matrix by using this condition. For instance, I could express the D in there. I could express it using this condition in terms of the B, C, and the A. But if I do this, then I have D equals 1 plus BC divided by A. Ah, okay. So construct charts. We construct two charts. The first chart we call U. And what is U? So a chart consists of a chart domain and a chart map. The chart domain is a subset of the topological space, right? So I need to define U as some subset A, B, C, D of the topological space. So it certainly needs to satisfy this condition. But it should really be, well, it could be necessary to have it as subset, and I claim it is necessary because I do this for A non-zero. Okay, so that removes some points from SL2C because there are SL2C matrices that have a 0 here. Okay, so this chart domain doesn't cover the entire SL2C. Okay, why do I do this? Well, now I look at the chart map I call X. X is supposed to go from the chart domain down to, and now let me see whether my intuition is right here. We go down to C3. So we do not, so our charts are C3 charts. And I take an element in U, and I map it by X, and I land here, so I have to take an element, well, X of, it's a bit funny notation, but let's be precise here. X eats such a guy, and I need to say what it is, and I write it down as a 3-tuple. Well, let me really write it as a tuple. This is C, C, C Cartesian product, so the result is a 3-tuple, and I choose A, B, C. So I look at such an element in SL2C, and I say the coordinates of this guy. This is a point in the manifold, in the topological space, but I coordinatize it by saying I only look at these three, and these are the three coordinates of this point. That's what I do. So you say, what about the D? Well, of course, the idea is I don't need the D, because if I know these three guys, by virtue of this being an SL2C, I already can reconstruct the D, right? Okay, so I have this. This is a map. It goes from here to here. I know SL2C being a topological space. I can then certainly decide what it means to go, and this is an open set, because I say not equal to 0. This produces an open set in that topology. And I can now decide on whether this map is continuous. Well, is it continuous? Yes, in that topology we constructed there, it's continuous to just look at this, and to write down this. So this is continuous. What you need to check? You need to check whether the pre-images of open sets are open. Pre-images of open sets here under this map are open here. This is the case. Okay, it's very trivial. Okay, this is continuous. Now, that's not enough. It needs to be a no, yeah, okay, fine, this is continuous, but I also want it to be invertible, so I need to restrict the target. It's true, this whole thing lands in C4, which is C3, I'm sorry, C, but I want to restrict the image so that I can now invert the map. Okay, that's what we always did. You interrupt me if you get lost, or okay? Okay. So the question is, what is the inverse of this map? Well, let's write it down explicitly. So I take the inverse of the x map. I start at x of u, and I go back to u. How do I do this? Well, obviously, I need to be able to feed the x inverse this triple ABC and to reconstruct from it an element in u. And this must be A, B, C. I take them immediately. And the D I reconstruct as 1 plus BC over A. At least that's what I said. So I take this 1 plus BC over A is the D. And you see this only works because I restricted the chart to have A non-zero. Yes?
Why is the set U open?
Aha. So, okay, open in what topology? Open in the topology on SL2C. The entire set is open. And I now have an inequality. Well, it's not equal to 0. I take this out. So the complement here, so the thing that I take out is the set where this equals 0. So one-dimensional subset of which you can check it's closed. You take out a closed one, the result is an open one. So you have to work a little to show this, but it's the case here. And that is because every lower dimensional subset, will be closed in that topology, in that standard topology. So you're right. In principle, you have to go through the motions to prove this. Well, then we'll need three days to do this, okay? But if you want, you can check. My guarantee to you, it is open in that topology. Okay? Okay. But I welcome the question, because that's what this is all about. We go through an example, and we have to see, okay, what do we have to do? And in some place, I'll have to say, okay, look, this can be done now. Okay? But it's not like it takes further techniques. You apply the standard techniques, you show this. Okay, it's good homework. Because we don't have a problem sheet this week, take this. Okay, so that's the inverse. We have this, and you can check again, because A is non-zero on that domain. On that domain, certainly, this is, again, a continuous map. So the map is invertible and continuous in both directions. That means X from the chart domain U into the image in the chart, in the chart, is a homeo. So local homeomorphism of the SL2C, it's a homeo, this guy is a homeo. In fact, it is a chart. That is, U with X is a chart of SL2C. But this chart doesn't cover all of SL2C because there are a number of SL2C transformations, namely all those with A equals 0, they're excluded, right? So there is no other way but to construct at least one more chart, and let's see whether we can cover, and it's really worth writing it down. Okay, so construct another chart. So let's call that chart V, and that is A, B, C, D in SL2C. And now I let the D be non-zero. And now my chart map, let's call it Y, from V to Y of V, which is certainly a subset of the threefold Cartesian product of C, be defined as follows. I take the Y and I apply it to A, B, C, D, but only from the set V. And I define this to be the 3 tuple of complex numbers. Let me think, if the D, I divide by the D, then I get the A, so I can forget about the A. So I take B, C, D. Okay, so now I only look at B, C, D. I say these are the coordinates, the first, the second, and the third coordinate of this guy on this domain. It's again the same business. You check the pre-images of open sets are open and so on. You check this is continuous. And you construct the inverse, y inverse from y of v back to v, y inverse now eating BCD. It eats these three complex coordinates, and it reconstructs this element of B of SL2C, BCD, but now you have to reconstruct the A that looks very similar. It's 1 plus BC by D. Okay, so the by D worries us, but we excluded it. Yeah?
One question. Why are you choosing the D this time? Because this doesn't give you a cover.
Pardon me? Because?
It doesn't give you a cover, so you can easily have a matrix with A and D being equal to 0 and still a part of SL2, C.
That's right. I didn't say it's the only other chart. Okay, but you're right. Okay, but then I'm only missing. Okay, then I need a third chart probably. That's the point. Okay, fine. So this is also continuous, and by the same arguments, it follows that Vy is a chart. Okay, and now you say, does the union cover? No, the union doesn't cover. And what I need is I need a third chart. UV, let's call it W. It's defined as before, but now for B non-equal to 0. And then we construct the coordinate map Z of A, B, C, D. And if I have the B non-zero, I can divide by the D, but then I can express the C. So I will have A, B, D as this map. And I construct the inverse of A, B, of this map Z. And it will yield the A, B, D. And the C I can reconstruct as AD minus 1 by B. Agree? Hang on. I take the BC to the right-hand side. I take the one there. Yeah. Okay. We may fail at mental arithmetic, but okay. Anyway, so this is this guy, and now by B, but now these three cover, that's obvious. So this is again a chart. So the same arguments every time. WZ is a chart. And now the overall result of this little subsection is that the union of U with V with W, this certainly covers SL2C, because the only point that's not covered now is where all four are 0, but that doesn't have determinant 1. Okay? So these three charts cover, not convinced? Yeah? Do we need the second chart? No, I see. You say if I have only these two, I cannot have the case that both of them are 0. You're right. Very good. Okay, so we don't need this one. These two already cover. Now, of course, there's no harm in having more charts, because we can anyway always extend the collection of charts, the atlas, to a maximal atlas. But you're right, it's not strictly needed. So the U and the W actually suffice to cover this guy. Are we happy? We're happy. And they're all homeos. And because I have, that also means that about every point of this guy, I have a homeo into some C to the 3. And from that, it immediately follows that SL2C with the already defined topology, we just checked facts for this topology is a complex three-dimensional, so complex three-dimensional manifold. So sometimes we would write, well, dim sub C with respect to complex numbers of SL2C is 3. There we go. We have a three-dimensional complex, I should say topological manifold. Topological manifold. Okay. So some people would call this, no, not yet. Okay, full stop. Good. Any questions so far? Yeah?
How would you notice if you had mapped in too much dimensions, like mapped in C4?
You would not be well, you would not be able to have a bijection then. No? You have a y and you have a y inverse. So if so you mean, okay, it could be this is a subset of C4, but one of the coordinates I never use, something like this. Yeah, no, okay, so that would be very silly. So that, but then you would have to have an additional entry here, right?
If you didn't notice that you could use the condition to kill one of the coordinates.
Yeah, but it's not so simple, because if you do this, this map, if you do this and you go back, you get more than SL2C. You see, if I can choose B, C, D, and A independently, that's the idea. If you're in C4, they're all independent. And then you can go back and you can construct A, B, C, D, but then you do not land in SL2C. You land in C4. So in principle, once you did this, you have to check whether you are in C4, because you're claiming you go back to V, and V is a subset of SL2C. And you need to check this here. Well, and it will fail if you just choose any A, or you mix up the A. You could use this A and write in there, that would fail. Okay, so then it's indeed this bijection property that is lost, because this map doesn't know about it. This map only knows about this restriction by encoding it explicitly here. Okay? Okay, so we have a complex three-dimensional manifold. So it's a topological manifold. If we want to see it's a Lie group, we need to check it's a smooth manifold. How do we do that? So what step is this? Step number? Pardon? E. Okay. So topological smooth differentiable manifold. So now we want to check that SL2C can be given an atlas A such that it is a differentiable manifold, a complex differentiable manifold. Okay. So how do we do this? Now, so far we constructed maps from the manifold, from the manifold into charts. But we know that in order to do differentiability, we need to see whether our charts that we have chosen allow smooth or C-differentiable transition maps. So we recall that we had charts UX and WZ that we wanted to use, and this one had to do with the A non-zero, and this had to do with the B non-zero. Well, that was the domain. It's written down precisely before, and we saw that this covers, so we know that if we take these two charts together, we certainly have an atlas, but let's call it the topological atlas, because that's all we know so far. By construction, there will be C0 compatible, these two charts. But now we need to check whether they're compatible, whether they're C infinity or C1 or whatever compatible. So check compatibility, yeah, well, C question mark compatibility of the charts in the topological atlas. There's certainly C0, but are there more? So what do? We consider a transition map. So consider the transition map Z after X inverse. Where does this start? It starts at the image of X, but of the intersection of U and W, because the transition map, of course, can only look at a domain that's the intersection of the two charts, and it maps you to Z of U intersected W. And now we need to construct this guy. Okay, I'm sorry, I need to write down again what the X inverse was. The X inverse took A, B, C, am I right, and reconstructed from it the point, which was A, B, C, 1 plus BC by A. Was that right? That's what we wrote down, okay. And the Z map, so that's the opposite direction, that took an element A, B, C, D in SL2C, and it mapped it to the coordinate triple, where B was non-zero. That is, I could reconstruct the C, is that right? So it went to A, B, D. Is that what we wrote down? Yeah, okay, thank you. Okay, so now we compose these two maps. So I start with an arbitrary point in here. So let's call that arbitrary point in the image of X, let's call it ABC. So we start somewhere in the chart image of the chart UX, and then we apply to it this transition map. Okay, and we want to check what the properties of this guy here are. So we let it act on the stuff it acts on, and because this is the chart domain of here, and the intersection with here, we know that the A is non-zero, and we know that the B is non-zero as well, because it comes from the intersection here, right? Okay, so fine. So with this understanding, let's just evaluate, well, not equal, it is already equal to. So we take the Z, after we made out of the ABC, we make this guy here. And then we take this guy and plug it in here, and follow this rule, right? So what we get is, we get the first entry up here on the left, but that's an A. Fine, comma. Then we get the second entry here, but it's this guy, it's a B. And then we get the entry down here, but that in this case is 1 plus BC over A. That's this guy. And now, of course, this guy here, so we could have written this differently. Where does it come from? It comes from C star cross C star cross C. But now the star is not the vector space dual or something. It means C without the zero element. I think we used this notation before. Okay, so this guy is from there. And now we have to check here. It is the chart domain of the Z, and the Z also says that the second guy, I think that's the same domain. It's C star, C star, C. Okay, so we have to check whether, is that me? Oh, okay, doesn't matter. Okay, so we have to check whether the whether this map, as a map from C3 to C3 on this domain, is differentiable. And you check, yeah, because the A here cannot be 0, this thing is certainly differentiable once, and you can check it's differentiable 2, 3, 4 times, and so on. Okay? So this thing actually is arbitrarily often complex differentiable, right? So, well, we just call it C differentiable. Okay? Even if you take the I mean, differentiability on C is stronger than differentiability on R. You could write this as 6 tuples of real numbers with the 3 real parts and the 3 imaginary parts, but then you also have to check whether these Cauchy Riemann equations hold and stuff like this. There are many ways to do this. Again, you can now delve in and really revise your complex analysis skills and so on, but this thing is C differentiable. Well, that's one transition map. There are only 2 charts, but don't forget, you also need to go backwards, okay? So we also need to check, similarly, check that the opposite transition map, x after z inverse, z of u intersected w to x of u intersected w, which you also need to construct, is also C differentiable. You'll find that is the case. So what do we have? That means that this topological atlas that we constructed happens to be more than a topological atlas, it's even a differentiable atlas. Fine. Now, if I have that, you can certainly define uniquely the maximal atlas, A as the maximal atlas containing, so the maximal differentiable atlas containing a top. So you put all the other charts that come to mind also in there that are to the desired degree of differentiability compatible with these charts. Okay, but we never do this explicitly. So this maximal atlas is more like the excuse later on that if you want to do a calculation, and for that you need a third chart that you would like the one we redundantly constructed, and you say, oh, darn, this should also be in the atlas, and I forgot this, so I mustn't use it. No, you can use it because, well, you can always maximally extend your atlas. That's the secret of the maximal atlas. You never write it down explicitly, but you draw an element out once you need it, and if you want to have a particular chart, you quickly check whether it's compatible with all the charts that are already in there, and then you may use it. Okay? That's the philosophy. Okay, so what do we have? We have, therefore, that SL2, C with this maximal atlas is a, well, it's a smooth manifold, it's a complex differentiable manifold, whatever. I write differentiable to arbitrary degree, C differentiable to arbitrary degree. Well, on C, if it's differentiable, we can anyway, what is it, Taylor expanded, Maclaurin expanded, and so on. So on C, this is very strong. Okay, so there we go. So at this point, we now can look at step F, and we can ask, is SL2C, which we can now think of as being equipped with a topology and a differentiable atlas, okay? We are not going to write this down all the time. We can take it and look at it together with the blob, which we already know is a group. That was one of the first things we checked, but it's a group where the underlying set happens to be, or has been made into by us, into a smooth manifold. So the question is this a Lie group? Is this a Lie group? Well, there we need to check something. Remember, a Lie group was a set with an operation that together is a group, we already know, such that the underlying set is a smooth manifold or arbitrarily often differentiable manifold here. But there was more. We need to check whether the two maps mu that take two elements of SL2C into an element of SL2C by virtue of the group operation. So let me call the elements just G, well, A, B, C, D, E, F, G, H, takes it to the result by the group operation. That's this map. We need to check that this map and this map I, that takes only one element to an element of SL2C, by virtue of A, B, C, D, by virtue of mapping this to the inverse. So that was 1 over AD minus BC minus D, A, B, C. We need to check that whether this map and this map are smooth. You see, I'm not very careful here with how often it's differentiable, and in the complex number, it's anyway a very strong thing, even if it's once differentiable. So anyway, we check differentiability to the desired degree, okay? We need to check this, but now we can check this, because look, for instance, at this I guy here. It is a map from a smooth manifold into a smooth manifold. Well, we know how to check whether a map from a smooth manifold into a smooth manifold is smooth. And we need to do this. And we also need to check whether, so now here you have the Cartesian product of two smooth manifolds. And I think it was on the problem sheet that these inherit a smooth atlas. This Cartesian product of two smooth manifolds inherits a smooth atlas from each of its factors. Right? So you make this into one big smooth manifold by inheriting the atlas to this Cartesian product. This is already a smooth manifold. So again, also this mu is a map from one smooth manifold, namely this big one, into another smooth manifold, the smaller one. But again, it's the same principle. Once you have the charts, you check this. But we'll carry it through in detail for the I. We want to check precisely that the I is smooth. So we have SL2C, we got the map I that sends an element of SL2C to its inverse between these two smooth manifolds, and we want to check whether it's smooth. Now, what you do for that, you need to look at only a chart in the domain and in the target. So let's say we start here, and then you need to do this for all charts until you covered the domain. Of course. So let's start with our first chart U in the atlas. So we restrict the map I to U. We only want to come from here, but I mean, we don't need to write this explicitly. It's clear by writing this here. I take this map, and now the question is, where do I land here? Well, the chart U comes with the chart map X, and you go into C star cross C cross C. It was this A left, the upper left entry being non-zero. Okay, that was this chart map. And so if we look at how this map I acts, now unfortunately I wiped it out, but was it not the case that this is A, B, C, D, and it maps this to 1 over AD minus BC of DA, they exchanged minus C minus B. That, I think that's the inverse. And now you see, if you start in the U chart where the A entry, well, I should rather say where the entry here is non-zero, you take this ABCD and you map it to here, but now you see in the result you only know the A is non-zero, but that's now this lower left, lower right entry, and we had this chart which we didn't need necessarily at the time, but which I called V. That was the chart that came with the chart map Y, and that was the one where this guy here was allowed to be non-zero, and that's of course exactly what you get as the image. Okay? So you can choose charts independently here and there, but you better make sure that at least you really map into that chart. So taking U and U again here, which in principle a possibility, you would have to restrict U here to those that, you know. Okay, anyway, so you go there, and so that's the, but then this Y map assigned which coordinates. I forgot that. So that was y, took then an a, b, c, d, and assigned it coordinates such that the d can be, no, such that the d can be divided. That means that the a can be reconstructed. So I think that must have been this map. Is that right? Can you quickly check your notes? That's what we did, no? Okay, so fine. So that means that guy goes into C, C, C star, because now it's the D here, the lower right, that is non-zero, so that goes to here. Aha, so chart here, chart here. Now I can construct this map, and that is y after I after x inverse. Aha. Okay. Well, strictly speaking, this of course only goes to the image. Oh, sorry. Aha. Okay. This of course only goes to the image x of u, which however happens to lie in C star. No, by construction. It doesn't happen to lie by construction. It lies here. And this goes to y of v, and that is just part of C, C, C star. That's the situation, right? And the nice thing is, aha, this guy here is now a map from some open region of this guy to this guy. And of course, I can also forget about the star. Well, it doesn't matter. It's a map from C3 to C3, well, from some region of C3 to some region of C3. And I can ask with standard analysis techniques whether this map is differentiable. Okay? And then I call this map up here differentiable. Okay, so let's do this. Let's construct this map. So let's look y after I after x inverse. What does this eat for breakfast? It eats guys in here, so we call them ABC. It eats coordinates in here, images there. Okay, so this equals, what is this? So we want to learn about this guy by virtue of its action. So first we take it by x inverse. We take ABC to, let's write it down, y after I applied to, well, very picky, you open brackets again, applied to A, B, C, and x inverse constructed 1 plus BC by A. Isn't that right? Right. Okay, so that's what this guy does. Now what does the I map do to that? So this goes to y of, small brackets, y of, and what does this eat? It eats the result of the action of the I map. But the I map takes first of all the 1 over the determinant of this guy. So this is A times 1 plus BC over A, so it's 1 plus BC minus BC. That's just 1. Okay, nice, okay. Times, I'm sorry, now this is overdone. So times, and now come these entries, it's the inverse, so it puts minuses here. It puts this guy up here, 1 plus BC over A. It takes this guy down here, and it takes the B here and the C there. Agree? That's what the inverse map does. Okay. Now, of course, we can simplify this a little because this factor in front here is certainly 1. And now we need to see what does the Y map do with this point. Well, it picks this entry, and this entry in this order and presents it as the coordinates. Not a problem. This one, this one, this one, in this order. Minus B, minus C, A. Ha! Great. The map whose differentiability you want to check eats ABC coordinates and spits out minus B minus C minus A. Well, if this is not differentiable, I don't know what is. Okay? So it's differentiable. So that means this map here is differentiable, and obviously several times, okay? So then we call I differentiable. That means the map I on the manifold level is differentiable. You see, here it's very tempting to say, come on, I know what this guy here is doing. It takes these numbers to these numbers, and that looks all terribly differentiable. Well, but that's because you now start pretending that you know what differentiation is at the manifold level. But of course, it isn't differentiable, because, for instance, what happens if AD minus BC, okay, it shouldn't go to 0, but okay. You don't know what differentiable is because you're not coming from a 4-dimensional space. You can't say, I look at I as a function of 4 variables and I check whether it's differentiable. Because it's a problem of 3 variables being differentiable, right? So you can decide differentiability here, but then you always have to keep in mind this constraint that AD minus BC is 1. Well, how do you mix that with your question about whether it's differentiable or not? Well, you have to decide, you have to distinguish between various cases when this is 0 and that is 0. Yeah, but that's exactly the chart construction. Okay, so you need to push the problem down with these charts. Okay, I was too quick here. So I have that this guy here is differentiable, but now, of course, I have to take another chart that covers this such that, okay, so we have this is differentiable. Okay, let's be very careful. Now, repeat such an analysis for the case where you now start with the chart W, because we know that if you check it for U and for W, you covered the entire manifold. Okay, you need to check what chart here you go to. Okay, as I said, the same thing. Then you have the Z here. This Z chart had the thing up there. That's the B, but the B goes with the C, so you can reconstruct the C. If you can reconstruct the C, that means you have the ABD. You go to ABD, but we said that the B, so this is in C, C star, C, something like this. Okay, you check whether I'm right or not, and so on. So you do the whole construction again, and you again check that this map down here is again differentiable. Okay, so okay, check also differentiable, and only now, because since SL2C is covered by U and W together, we can then conclude that the map I up there is differentiable. Now we have to do this for a system of charts that cover and come from a differentiable atlas. Okay? Aha, so we found that this inversion map is differentiable, and similarly, using the atlas, using the differentiable atlas defined on SL2C cross SL2C by virtue of the differentiable atlas A on SL2C, so inherit this, I remarked this before, also show that mu is differentiable. Okay. So see, if you're really skeptic, it's a lot of work to check this whole thing as a Lie group, right? It doesn't come entirely for free. But we know that we can do this. We have confidence we can do this. And so we have as the first, after more than an hour, we realize that SL 2, C with this group operation is a complex 3-dimensional Lie group. Okay. It's actually the only example so far I presented of this. So you saw I rushed through this Lie group and Lie algebra theory without giving many examples, because you see, to construct such an example, you have to invest some effort. But now, okay, good, good. So what's next? Well, we want to construct the Lie algebra of the Lie group. Where were we? E, step F, is that right? Let's say step F. F. Okay. G. G. Well, what's the Lie group? A Lie algebra. L of SL to C of the Lie group SL to C. Okay. So first of all, L, okay, L of SL to C. There's lots to write, so usually one writes this small s small l of 2C. It's just notation. So if you have a Lie group and it carries a capitalized name, which it always does, then the corresponding Lie algebra carries the we call this the small letters, right? SL to C. Okay, that's just terminology, okay, notation. But now we need to think hard again. What is this L of SL2C? Well, recall that the Lie algebra of a Lie group, the Lie algebra of the Lie group as a set, it was the set of all left invariant vector fields. So it was X was a vector field on the group, a vector field, so it was a section of the tangent bundle, vulgar vector field, on the group G, okay, that was left invariant. What was a left invariant vector field? Well, we had these left translations, LG. How were they defined? They were defined as LG took an element. Okay, so let's write it down for our case. We take an element of the group. In our case, this is a point of this sort, and it then takes one element of the group and produces another element of the group by virtue of L, A, B, C, D, eating E, F, G, H is defined as, well, you know, the matrix product from the left. That's the point, so use the group operation E, F, G, H, and this map here is called the left translation. But then you have a map from a smooth manifold to a smooth manifold. It is, after all, the mu, well, it's part of the mu map because you fix one entry, but you can show by virtue of the definition of the atlas on the Cartesian product that this guy also is a smooth map from SL2C to SL2C. If it's a smooth map, there exists an associated push forward of this map, and you can take a vector field H, and you can look at it at the position X, and you can look at it at some point H in the group, and you can require that, so if you act on it like this, then the whole result will be where? The whole result will be at LG on H, which is GH. It's the group operation in between here. And you can require that this is what the vector field at that point already was, GH, XGH, and that's the set of left invariant vector fields. Left invariant vector fields. Okay? And obviously here G, wherever I wrote G, this is in our case SL2C. That was the definition of this Lie algebra. So you really need to look at the whole group manifold and look at vector fields on there. But we saw that there is an isomorphism. Recall that there is an isomorphism between the tangent space at the identity. So did we call this guy id? So id in our case is, well, the tangent space at 1, 0, 0, 1 to the group to SL2, C as a vector space is the same as the Lie, as the left invariant vector fields of SL2C. Do you remember this result? Aha. Now, why is this interesting? Well, it's interesting because rather than looking at vector fields, even though very special vector fields on the entire group, I rather look only at one vector in the tangent space or another vector in the tangent space. But how can it be that this guy here, this is after all a sub-vector space of all vector fields, but this is as an R vector space, or in this case as a C vector space, as a complex vector space, this is infinite dimensional, but we saw that this is finite dimensional. Indeed, SL2C is three-dimensional, so the tangent space is three-dimensional. How can it be that as vector spaces they're isomorphic? Well, this is a very strong condition, the left invariance. Okay? But you see, this guy here has an advantage over this guy here. This is easy enough to see. So let me draw a picture. I don't know whether it's a good picture, but so assume we had a group manifold that's, well, assume we have the S2. Well, that's not one of the guys we're looking at the moment, but imagine the group looks like this, okay? And now you go to the identity, let's say that sits here, and then there's the tangent space here. Now you can look in all possible directions here, but you only have one vector. Now, the advantage of this guy, of the left invariant vector fields, so say you have a vector field on here that looks like this, and which at the identity corresponds to one particular vector, I mean the vector that's part of that vector field here. If you have this entire vector field and say you now have yet another vector field there, so you have another vector field, another left invariant vector field on the manifold. Apart from the white one, we have also a green one, and at that point in that tangent space you have this white vector and this green vector. Now, if you look at the entire vector fields, they're vector fields, and you can take the differential geometric bracket there, right? Between two vector fields here, you have the bracket from differential geometry, which takes a vector field and another vector field, and we check that this is again a vector field, okay? And that's defined. But this bracket you can only calculate if you have an entire vector field, because that is one vector field acting on the other, acting on a function. So in a sense, you look at the change of one vector field with respect to the other. But at one point, you cannot do this. You could apply the white vector to the green vector field and you get a result. But you couldn't then take the green vector field at that point, so that means that green vector, and apply to just the white vector. That doesn't give you a result because you need to derive. So you need a white vector field, you need a green vector field, and then you can calculate between the vector fields, you can calculate the commutator, right? Now, if you restrict attention to just that one point, how on earth do you inherit a commutator over here? You need to get a commutator, well, you need to get a Lie bracket. This is the differential geometric commutator. You need a Lie bracket here, and we constructed this guy. It was the double bracket. Well, only for notational purposes it was a double bracket. So also recall that we defined a bracket written like this. on T id SL2C, well here at least we do this, T id SL2C cross T id SL2C into T id SL2C. Okay? How? Well, we take a vector, well, let's call it A. It's just a tangent vector to SL2C at the identity. And I take another such tangent vector. And now I need to say which tangent vector at that point is this supposed to be. And the idea was, well, I can use the differential geometric commutator that eats to vector fields. But so I need to construct from the white A vector at this point. So it's just the A in this tangent space and the green B vector at this point. I need to construct an entire left invariant vector field from this A. And how do I do this? Well, that was not so difficult. This is just the push forward of the left translation of this A. And remember, as I just said, or as this indicates, this A sits at the identity of SL2C, right? And then I act with this guy on it for an arbitrary G. And then I'm at an arbitrary point G, and I mean the vector field that's defined like this. So maybe, this is clear enough. So, and then I also push forward the B, which also is just another vector in there. And I do this for all possible G, and then I get a vector field here. Okay, notation is a bit funny because there shouldn't be the G here, there should be the abstract field, but you know, for all G, this gives you a vector field. Okay, aha, so I can choose an arbitrary tangent vector here. Now this is a bilinear bracket. That's obvious that this is bilinear. So I only need to know how the bracket is defined on a basis of the tangent space. Is that right? And if I want to make life simple, I choose coordinates. Well, if I want to calculate something, I need to choose coordinates anyway. And so it suffices, and so I could use the coordinate-induced tangent vectors here, right? At this point at the identity. But then I push them forward to make out of them an entire vector field, and I fully determine this bracket. Okay, let's try to do this. So task, determine the bracket. Or in other words, determine the structure constants of this bracket. Okay, so now how do we have to go about this? We have to calculate the push forward of some vector at the identity. Aha. So let's try to calculate that guy. So let's try to calculate L sub G. So G is some element of SL2C. So I write here L, A, B, C, D. And I take the push forward and I act on D by D. So now I need to choose a chart that contains the identity. The U chart contains the identity. U only asks you A to be non-zero, but in the identity A is 1. So I can use the U chart, because that guy covers the identity, since, so the UX chart, since 1, 0, 0, 1 is an element, is covered by the U. So I take the U chart with its x coordinates, and these x coordinates, they run from 1, 2, 3, so I can act on the ith tangent vector, and you know we always have to say where, well, at this point, at the identity. Okay? I act with this guy on that guy, and of course the entire result will be a vector, namely the pushed forward vector. Where will it live? It will live at this guy times this guy, group operation wise, but that's A, B, C, D. So I take a tangent vector at the identity, the ith tangent vector in this coordinate system, but it's just clever to use that. Okay? And then I do this for I equals 1, 2, 3. For I equals 1, 2, 3, I can calculate this guy, and this calculates this first bit. That's the idea. Okay? I take this at the identity, I push it forward to this point to get a tangent vector at that point. And I can do this for any point A, B, C, D in SL2C, well, for any such point in U, that is. And of course, I get then from this one vector, I construct this way the entire vector field that comes, left invariant vector field that comes from there, because we check that if I do this construction, the result is a left invariant vector field. Okay, so now I need to calculate this push forward. So how do you calculate the push forward? Well, you check what is its definition. This is a vector field. Where is it? The map goes from SL2C to SL2C, this guy. So you have to act on a function that lies in the target. Well, that's again this thing. You act on some f. So for any f that is a, say, smooth function on SL2C, we act on this, and that way we want to find out what kind of vector field this is. Equals. So now we apply our definition. What's the push forward of a vector field? It is the vector field d by dxi at 1, 0, 0, 1, acting on f after the map, the smooth map underlying the push forward. But that's the map L, A, B, C, D, without the star. This is this guy. That's the definition of the push forward. Okay? So, now we want to calculate this. Do you remember what this was? Was this a partial derivative? No, it was not a partial derivative. It used specifically these coordinates. But how did we translate this guy into a partial derivative? Well, this was a partial derivative, but only by taking the ith partial derivative, acting on the function behind, well, in this case is f after L, A, B, C, D, after x inverse, the entire x inverse map, but then the ith derivative. You see, I used the x and I used the I. This was the definition. And this is the partial derivative on a map. Let's check from where to where does the map go. From x inverse, that means it goes from x of u, which, however, is a subset of C star cross C cross C. Aha, very good. Goes into, you go to a point. You go to a point in the manifold in SL2, then you make a left translation, okay, you stay in SL2, and then you have a function that takes you from SL2C into the complex numbers. So I should say this is a function that goes, of course, into the complex numbers. Aha, okay, very good. This is a function from C3 or some open part in C3 to C. I can definitely take the first, the second, and the third derivative, the derivative with respect to the first entry, the second entry, and the third entry, and this is what this guy means. In a Cartesian product, this tells you which slot you take the derivative of. This here tells you much more. It tells you there is a chart in between, a chart map, and that's why you have to write the x. Now I remind you that we agreed that you saw this symbol very often before, but wherever you saw it, well, apart from in differential geometry, wherever you saw the symbol before, it was illegally used in our notation. This is what should have been used always, and this is a very special symbol. Okay? You remember I made quite some point out of this. If you forgot, ask in the problem class or go back to the notes there. So the nice thing here is these abstract definitions, they actually now are filled with our special definitions of this product on the group. Well, we'll come to that. Let me continue here. So we have this guy. Okay. So we have this guy. Now, so this makes sense. But now I want to go one step further, and I insert yet another pair of chart map and inverse chart map. I write del I, Li of f after x inverse after x. Well, that obviously has no effect, right? After L sub a, b, c, d after x inverse. Very obviously, nothing at all happened. Okay? Right. So, but now I can choose the associativity of the circ, and I find that this here is a function that goes from C, well, from some part of C3. Well, let's not be so picky here. The only thing I want to check is whether we can do this by standard analysis rather than manifold theory. C3 to C, and this guy here, it goes from some part of C3 via the manifold down to C, some part of C3. That's the situation, and there is a composition in between, and there is a derivative. It's multidimensional, so we need the multidimensional chain rule. But we can use the multidimensional chain rule. So how does it work? So that's the outer derivative, and that's the inner derivative. Okay, so this is del m of f after x inverse to be evaluated at x after L, a, b, c, d after x inverse of, well, where actually? So let's go back. We evaluate this guy up there. That's a vector field as at f, at a, b, c, d acting on f. That means you evaluate at a, b, c, d, right? So you should write here that, no, hang on, that's not true. No, that's not true because we evaluate at 1, I was 1 before. I evaluate at 1, 0, 0, 1. I evaluate at the identity. I evaluate at the identity, right. So I should have written here, this is the vector there, and the full definition of this guy is that it then evaluates at the point, so it evaluates at x of 1, 0, 0, 1. Right? If there's a del by del xi at the point P, then this is evaluated at, in the chart, at the coordinates of that point. Agree? So it's at that point. And so here it must say all of this is evaluated at the point x of 1, 0, 0, 1. Okay? And so that's here the point x of 1, 0, 0, 1. Well, the x itself is a triple. You know, it is 1, 0, 0 are the coordinates of this point. But let's write it here like this, because you see now immediately comes the x inverse, so it would be silly to write here. Okay, anyway, so that's this. And then comes a times, and this is the times in the complex numbers. Okay, now you need to take the mth component of this guy. But what is the mth component of this guy? This is xm after L, A, B, C, D after x inverse. And so that's this function. And okay, I wrote a bit too high because I wanted by custom I wanted to do a fraction type thing to write d by d, but it's not right because now again it's this del I from here. This del I goes to the inner derivative, but the mth component, and the outer derivative is the mth derivative, not the mth, the derivative in direction m or of component m of this outer function. It's the multidimensional chain rule, and it's this del I here, and the whole thing is evaluated at x of 1, 0, 0, 1. So this is nothing but the multidimensional chain rule, which you learned in the first week of your studies. Okay? Just properly applied here. Aha. What do I want? Yes. So let's look at this guy here. I feed into this function this x of 1, 0, 0, 1, but then it's eaten by the x inverse, so up to here, the 1, 0, 0, 1 pulls through to here. The left translation on 1, with respect to a, b, c, d, on 1, 0, 0, 1, however, so let me write it. So this is 1, 0, 0, 1, then acts the left translation on it, and then it becomes a, b, c, d, obviously, and then acts the x on it, and then it becomes the tuple ABC, the triple ABC, because these are the coordinates. Do you agree? So this guy is to be evaluated at this point. But I rather write this, I do not do the last step, so I write that everything here is x of a, b, c, d. That's also true, and I could evaluate this. But I don't, because I now look at this first factor, del m f after x inverse evaluated at x of a, b, c, d. Well, this is nothing but d by dx mth x at the point a, b, c, d acting on the function f. This is this first part. Do we agree? Up to here. This is this guy, right? Because if I present you with this, you say, that's the del m on f after x inverse at position x of a, b, c, d. Yeah, that's what's written here. Okay, so we go the step back here again, but you see it's not undoing this whole thing because I inserted this identity and I took this part and I separated this off, and here I end with this. And this is, of course, so now I have a multiplication, a complex multiplication, and now comes the second part here. And this will be the interesting part. We'll see in a second. Yeah, we should evaluate this too. And how do we do this? Well, before we can take the derivative of this map, we should maybe write down this map. Okay, so consider xm after L, A, B, C, D after x inverse, is that right? Yeah. And you want to study this map. Well, you study a map by seeing how it acts on the domain. The domain is something like x inverse, something like ABC, because it obviously acts on some x of u, and I have the ABC. So now study this map. What is it? Well, equals. Well, we can again go step by step. So the x inverse acts on this, and it makes out of it the ABC 1 plus BC over A. Legal? Yes, legal, because we look at the chart U. The chart U is good enough. After all, we're only going to be interested about points near the identity. That's this guy. So, okay, bad idea. ABCD is my, okay, thank you. So, EFG, I apologize, so EFG, 1 plus FG by E, right? I think so. Okay, so then you can act with the left translation on this guy. So what do you get? And now you see, at this point, the group law, this funny, strangely defined group law, which we're familiar with from matrix multiplication, but here it enters the whole thing. Now think about, we're trying to get the Lie bracket or a Lie bracket on the tangent space. We induce it from here. What on earth does it have to do with the group? Well, this, when I now apply this to this by means of left group transition, this is where the group law, the very specific group law I used, enters the whole thing and inherits all it has to say to the Lie algebra. This is the point. Okay? The rest is all formal dressing. Well, we need the formal dressing, otherwise we don't know what we're doing. But this is the point where the group structure is injected into the whole thing. Okay, so AE plus BG, AF plus B1 plus FG over E, CE plus DG, CF plus D1 plus FG over E. Correct? Good. And finally, I look at the mth coordinate of this. I look at the mth coordinate. Well, so I can write down all the coordinates under the x chart, and then I pick the mth one from it. Otherwise, I have to write it down for 3 now. Okay, so how does the x take this guy? Well, the x takes this one, and this one as a coordinate. AE plus BG, AF plus B1 plus FG by E, and CE plus DG. Good. What do we do with this? Well, this guy is to be differentiated with respect to the ith entry it has, and then evaluated here, to be evaluated here. So let's do that. So then, or therefore, we can look at del I of this entire line and evaluate it at the point x of 1, 0, 0, 1. Why? Well, because we're still lacking the second factor here. Second factor. Good. The ith entry. But you see, the ith entry, if I equals 1, it means derivative with respect to E, if I use this formula. Second entry is derivative with respect to f. Next is, do you see how bad it would be if I wrote here d by dA or something? Then I'd be totally confused. It instructs us to derive this with respect to the ith slot it acts on. Now I know what that is. Okay, so how do I do this? Well, I do this somehow component-wise. So this thing has an m in it, so it depends on m. Let me write it out, otherwise we get into trouble. xm after L, A, B, C, D, after x inverse, to be evaluated at x 1, 0, 0, 1. But now maybe this x 1, 0, 0, 1, we should really write it as 1, 0, 0, because that is what it is. Okay? We evaluate it there. And so what is this? Well, the result will depend on the m and it will depend on the I. They're open. So I may, if I wish, choose the symmetry of numbers. And I say I write mi, and this guy here is the row, and this guy is the column, and this means nothing but writing down these numbers in a systematic way. Okay? Nothing else is implied by this. So I first fix the m to be 1. That means I look at this first entry. That's m equals 1. And that means I'm in the first row. So I now fill out the first row. And I take this first entry and I derive it with respect to first to E, then to F, and then to G. So the first one with respect to E is A. Done. The first one, m equals 1, with respect to the second entry, I equals 2, f is 0. And then the first one, first entry, with respect to the third, with respect to the g, is b. Okay, first line done. We are confident we can do this in general. So we look at the second one. This is this guy. We derive with respect to e. Aha, not a problem. This is minus this thing by e squared of b1 plus fg. Agree? Now we take, again, the second. We derive with respect to the f. That's not more complicated. That's bg by e. bg by e. Agree? Okay. You should really check my my calculation here. Pardon me? Ah, AF. Oh, yeah, very good, very good. Thank you, thank you. Plus A. So the moment I encourage you, you find a mistake. Okay, good. So, and then the second one with respect to the G is simply BF by E. So I really hope that all of this is right because, well, it's an adventure for me too. So it's this, and now we take the third one, that is this one. We derive it with respect to the E, that's a C. We derive with respect to F, that's nothing, 0. And we derive with respect to G is a D. Aha. So we calculated all these numbers for every I and every M. Well, and we take this matrix, well, matrix, this collection of numbers, Mi, and we put it here. And of course, there is a summation over the m's. Why? Well, because it was here, summation over the m's. And the result depends only on I. Ah, that was the ith tangent vector at the identity we put in. I with respect to the chosen coordinate system. It makes sense that there's an I left. And for every xi, d by dxi, I get another result, namely this. So what does this all amount to? Ah, pardon me?
Can we just evaluate it right now at 0.100? Because that's what we still have to do.
Ah, you're right, absolutely. Oh, okay. So let's see what we're doing here. So I should definitely not delete this. We push to the point A, B, C, D. And we evaluate there, and we evaluate here. But hang on, I wanted to have a vector field. Aha. So now I've got to be careful. So after all, what I wanted is I wanted a vector field defined at every point A, B, C, D that belongs to SL2C. And I generated this from here. So if I leave A, B, C, D undetermined, I have a vector field. Now, I was already happy because I have here a basis of a vector field at the arbitrary point A, B, C, D. Ah! But then this wouldn't depend on... Ah, no, okay, I mean, okay, if we calculate right, we have to evaluate. Okay, I agree. So we evaluate at 1, 0, 0. Okay, very good. Thank you. Thank you very much. Okay, now we got to be careful. Yeah, but these are the entries that are handed to us. So they are the EFGs. But why are there still ABs? Ah, no, of course. Yeah. Very good. Thank you. Okay, so E is 1, but the F and the G are 0. Ah, that's good because that survives. Okay, so we have A, 0. Yeah, very good. B times 1 plus 0 is B by 1 is minus B. E is 1. G is 0, it's just an A. Yeah, very good. E is 1, F is 0, is nothing, 0. And C remains 0, D. Ah, very good, very good. You saved me. Okay, M, I. Much simpler, much simpler. So these, of course, this is the only stuff that now depends on the point where the field is. And you see this guy acting on an F yields this guy here. So now let me take this down here again. So now it's much easier to write down our final result here of this calculation equals, so I acted on this F, and now because this is a complex multiplication, I can write d by dxm at the point A, B, C, D of SL2C acting on an F. I put the F to the right-hand side like it is there, and in front of here I have this factor matrix, Mi, and it's A0B minus BA0 and C0D. Aha, there you go. So what did we find? Let me try to squeeze it here. We found that the push forward L sub A, B, C, D push forward on the ith coordinate induced vector at the identity. So this vector at the identity is being pushed forward, and of course yields a vector that's defined at A, B, C, D equals, so I leave out the F because I can leave out the F here, and I do it now for the first vector, x1. That means I equals 1. That means the column is 1. That means I have to read down this column. This equals A d by dx1. But this is the tangent vector coordinate induced at A, B, C, D minus B times d by dx2 at A, B, C, D plus C times d by dx3 at the point A, B, C, D. Right? This is the tangent vector in the one direction at the identity. I push it forward to the point A, B, C, D. There it becomes a linear combination of the natural, of the coordinate-induced basis at the point A, B, C, D with the coefficients components A minus B plus C. And so the same is true if I write here, so everything stays the same, but I write d by dx2, and everything else is the same, equals, and then it has the factors minus b, 0, a, so there's only the a factor here. No, minus b was right. No, 0, a, 0. So 0, a, 0. So there's only a times d by dx2 that is at that point. And the final one is the push forward of the x3 at the identity, this whole dressing up here, and you get b0d. So you get b d by dx1 at A, B, C, D plus d times d by dx3 at A, B, C, D. Well, do we have a vector field or don't we? Well, we do. Okay, so we constructed from a single tangent vector at the identity, no, from three very different, for I equals 1, 2, 3, tangent vectors at the identity, we constructed 3 vector fields. Aha! And now we can go up here to the double bracket and calculate it. So I can now calculate, I take the double bracket of dx. Well, let's do a specific example. I can take the first one, at the identity, because that is where this bracket should act, and I can take the second basis vector, x2, at the identity, and for this bracket is defined. That's the A and that's the B. Well, but this is defined as the differential geometric commutator bracket L, A, B, C, D, push forward of this d by dx1 at 1, 0, 0, 1, comma, L, A, B, C, D, push forward of the second vector to this point A, B, C, D, starting here with a vector at the identity. But now this is a vector field and this is a vector field, so I can now use the definition of the differential geometric bracket. Well, I can act on an arbitrary function. That always makes life simpler, but because it's arbitrary, I can just apply. It's L, well, it's this guy, but we know how this guy looks like. This is A minus B plus C. This is A minus B plus C. Well, d by dx1, but now at A, B, C, D. And these are related, these A, B, C, Ds. d by dx2 at A, B, C, D. And this is C times d by dx3 A, B, C, D at these points. That's the first vector field. And the second one, you plug in the same. That's A d by dx2, happens to be a little simpler, at point A, B, C, D. Okay, you act on an F. And how do you do this? Well, you know this is an abstract. Well, I just do it. This is an X. And this is a y vector field, and you know that this whole thing is xy minus yx on f. What does that mean? Well, you first apply it like this, then minus y, you apply it like that. But now you use specifically this guy here. Well, how do you, well, first of all, this is multilinear. Well, be careful, only R linear, not C infinity linear. You execute this, and of course you will always meet guys of this form, d by dxi at position A, B, C, D, acting on f. But you know what that is. That's del I of f after x inverse evaluated at x of A, B, C, D, but that's A, B, C, D. Right? So these guys will appear everywhere. You plug them in here, and you will come to a result. And, bad definition. Of course, I forgot something. Not so bad. Nothing happened. Here, I want to be again at this point, so I need to also do the back translation. I need to go backwards again. But that's also not a problem. That's just L G inverse push forward. I push it in the opposite direction again. And of course, the left translation has an inverse. That's obvious. You can check that L G inverse is the inverse of the left translation. Very quickly seen. So I have to put this thing here, because only then are we back to this point at the identity, because you see what would come out here would be a vector field, but at the point A, B, C, D. But we want to have a vector at the identity again. So we have to plug in here L, A, B, C, D inverse, push forward. And of course, we know how to calculate A, B, C, D inverse, and we know very, very simple. Okay, so this has to go everywhere here. This is L, A, B, C, D, inverse, push forward. And so you calculate this L, A, B, C, D, inverse, push forward. You calculate this, and what you will get a certain linear combination, homework, flower, d by dx1 at the identity, plus pine tree, d by dx2 at the identity, plus, who knows, star d by dx3 at the identity. Very good. Because if you now, so we did this for 1 and 2, and of course, what you read off from these coefficients, you read off the structure coefficients C, 1, 2, because we had 1 and 2, and then here this M, and that is flower, pine tree, star, the mth component. So from this calculation, if you do it with the first and the second here, you get these structure coefficients with down 1, 2, and C1, 2 is flower, C2, 1, 2 is pine tree, C3, 1, 2 is star. And then you do this for the other two independent combinations, and what do you get? You get the structure coefficients of small SL. So you do this for all combinations there, and you get the structure constants of SL2, C. Please do this as a homework, but you see this is now just simple, a simple calculation. It's 2 lines. Time is up. And there we pick up next time, and we'll derive the Dünkin diagram of the SL2C algebra. Okay, thanks.